Wave propagation, problems on propagation modes, series on antennas and wave propagation, lecture number 6.20. A wave can take any one of three forms or modes while propagating from transmitting antenna towards receiving antenna. These modes are ground waves, sky waves and space waves. The mode wave assumes depends mainly upon frequency. When frequency of the wave is below HF band, then usually the wave takes the form of ground wave. When frequency of the wave falls within HF band, the wave travels in the form of sky wave. When frequency is above HF band, the wave propagates, travels, moves towards the receiving antenna in the form of space wave. In the present session, we consider several problems and their solutions too, which are based on the three modes of wave propagation. The solutions of these problems are described, explained, and discussed to give a clear understanding into the propagation mechanisms of electromagnetic wave. We begin the session with a problem, example 1. This problem is set on ground wave propagation. An antenna with the effective height of 150 meters is transmitting at a frequency of 1.2 megahertz, carrying a current of 8 amperes. If the receiving antenna is situated at a distance of 40 kilometers away with a height of 2 meters, find the voltage induced over it. Voltage induced over a receiving antenna, it is given by the formula V is equal to 120 pi HT HR I lambda D. HT HR in this formula refer to effective heights of transmitting antenna and receiving antenna. I is current over the transmitting antenna. Lambda is wavelength of the traveling wave. D is the distance between the antennas. HT, HR, I, lambda, D. All are given in the problem. Lambda is not given directly. Frequency is given. From frequency, lambda can be obtained. Solution. Frequency of operation 1.2 megahertz corresponds to a wavelength of 250 meters. Notice lambda is C by F. F is given. C is 3 into 10 power 8 meters per second. So lambda can be found without any difficulty. In the present case, it turns out to be 250 meters. Substituting these values, we get a value of voltage induced on receiving antenna as 120 pi into 150 into 2 into 8 over 250 into 40,000. 40,000 is distance between antennas. 40 kilometers is given. When we convert it into meters, it becomes 40,000. A little bit of simplification gives voltage over receiving antenna as 90.5 into 10 power minus 3 volts. Another problem, example 2, this is also based on ground wave propagation. A short monopole of length lambda over 100 located over a conducting plane is carrying an average current of 1.5 amperes. Determine field intensity at a distance of 1 kilometer and also maximum voltage induced when a 0.75 meter long vertical monopole is located there. It means at a distance of 1 kilometer. We are asked to determine two things. One, field intensity at a distance of 1 kilometer. We are also asked to find voltage induced over a vertical monopole, the receiving antenna, when its length is 0.75 meters. First, field intensity. Solution. Field intensity is given by this formula. E is equal to 120 pi HT I lambda D. Lambda is wavelength, D is distance of the field point. HT is effective height of the transmitting antenna, I is the current. Current is given, height is given, lambda over 100. Of course, frequency is not given, lambda is not given in the problem. D is given 1 kilometer. With the given data, let us try to find out E, field intensity. E is 120 pi into HT. HT is lambda by 100. So lambda 100. Current is 1.5. I is 1.5. Lambda is lambda in the denominator. D is 1 kilometer. Therefore 1000 meters. Lambda gets cancelled. A little bit of simplification gives us the E as 5.65 millivolts per meter. So one part of the problem is solved. Second part is maximum voltage induced over a monopole, vertical monopole, 0.75 meter long monopole when it is placed at a distance of 1 kilometer. Induced voltage is maximum when the receiving antenna is oriented parallel to E vector in the incident wave. In the incident wave, if E vector is vertical and monopole is also vertical, then maximum voltage gets induced. So V is E into HR. E has already been calculated. It is 5.65 millivolts per meter. HR, effective height of receiving antenna, 0.75 meters. It is given. Multiplication gives us V as 4.24 millivolts. This is the answer to second part of the problem. Another problem, example 3. This is also based on ground wave propagation. A 0.3 megahertz ground wave 750 meter link is established using two identical short monopoles when the average current over transmitting monopole is 2.5 amperes and minimum signal strength required, here required should be there, required at receiver is 1.5 millivolts. Determine height of each dipole. Transmitting antenna and receiving antenna both are monopoles, short monopoles. Their heights are, it is given that they are same, heights are same. Small correction, it should be monopole, height of each monopole. Current over transmitting monopole is given as 2.5 amperes. And distance between the antennas is given as 750 meters. Frequency is given as 0.3 megahertz. Minimum required signal strength at the receiver is given as 1.5 millivolts. With this information, let us try to find a solution to get the answers. Monopoles are identical and hence their heights are same. It is given. So HT is equal to HR equal to, let us say, H. V, voltage induced over the receiving antenna when it is ground wave. It is given by this formula V equal to 120 pi HT HR I by lambda D. We assumed HT is H, HR is also H. Therefore, this product, HT HR product becomes H square. I remains as I. Current over the transmitting antenna. Lambda is wavelength of the wave whose frequency is 0.3 megahertz. It can be determined within no time using the formula C by F. F is 0.3 megahertz. C is 3 into 10 power 8 meters per second. So it is, lambda is available. D is also given 750 meters. So V is 120 pi H square I by lambda D. This is the relation when we implemented the general relation to the specific case of identical height antennas. From this relation, H square can be found equal to V into lambda D by 120 pi I. It gives H square equal to V. V is 1.5 millivolts. Lambda is 1 into 10 power 3. This value we got using lambda equal to C by F. And D is given as 750 meters. 120 pi in the denominator multiplied by I equal to 2.5. Now simplification of this expression gives us h square as 0.12. It gives us h equal to 0.345 meters. So height of each antenna, effective height of each antenna, in the present case it is said they are monopoles. Height of each monopole requires to be 0.345 meters. Now we move to another mode, wave propagation mode, that is sky wave propagation. We begin this mode with a problem, example 1. Determine plasma frequency f of fp, permittivity epsilon and refractive index n when layers electron density is 10 power 4 per cc at 10 megahertz. Solution. First we have to convert electron density into MKS system. N is given as 10 power 4 per cc in meter cube. Per meter cube it becomes 10 power 10 per meter cube. Then plasma frequency Fp can be found using the formula Fp is equal to square root of 81 n. N is available. Substituting the available value for n in this expression, we get Fp as plasma frequency as 9 into 10 power 5 Hz, or it is 0.9 megahertz. Now permittivity epsilon, refractive index n can be computed. Permittivity is product of two factors, absolute permittivity, relative permittivity. Absolute permittivity is epsilon naught, relative permittivity is 1 minus Fp square by f square. Fp stands for plasma frequency, which we have just computed. It is found equal to 0.9 megahertz. Frequency of the wave is given as 10 megahertz. So using these values in this expression, epsilon permittivity can be found as 0.9919 epsilon naught. So relative permittivity here is 0.9919. Now refractive index. It is equal to square root of epsilon r, relative permittivity. Square root of 0.9919. It turns out to be 0.9959. This is the refractive index. Another problem, example 2. This is also based on sky wave propagation. A wave is incident on a denser medium at an angle of 30 degrees from free space. If the angle of refraction is 20 degrees, find velocity of wave in the denser medium. So this is free space. This is denser medium. It is incident at an angle 30 degrees. Angle of refraction is 20. This is 20 degrees. Find velocity of wave in the denser medium. Here he wants velocity of the wave. Solution. According to Snell's law of refraction, index of refraction is n is equal to sin I by sin r. This is Snell's law of refraction. Index of refraction is equal to speed of wave in free space over speed of wave in the medium. From this relation, speed of wave in the medium becomes equal to sin r over sin I into speed of wave in free space. Speed of wave in free space is 3 into 10 power 8. Sin r is sin 20 degrees, sin I is sin 30 degrees. After simplification, ultimately we get speed of wave in the medium as 2.05 into 10 power 8 meters per second. This is the answer to the problem. Another problem on sky wave propagation, example 3. A single hop skywave communication link is connecting 2 points on at a distance of 1500 kilometers using an ionospheric layer located at a height of 300 kilometers. If the critical frequency is 7 megahertz, find maximum usable frequency for the 2 points. Here are 2 points. The distance between these 2 points, 1500 kilometers. These 2 points are over the surface of the earth. A layer is there at a height of 300 kilometers, somewhere here. This is 300 kilometers. A link has been established like this. Let us say this is transmitting antenna. It releases wave. It goes, hits the ionospheric layer. There it gets refracted back to earth like this, traveling towards the receiving antenna. It is given critical frequency is 7 megahertz for this layer. We are asked to find maximum usable frequency for the 2 points. Solution. Maximum usable frequency FMUF is related to critical frequency FC through a relation. That relation is given here as maximum usable frequency is equal to critical frequency multiplied by secant phi I. Phi I is angle of incidence. We are asked to find maximum usable frequency FMUF. We need value for this. FC is given. Critical frequency is given 7 megahertz. To find FUMF from this relation, the thing that we need right now is phi I. Given critical frequency is 7 into 10 power 6 hertz. This one. Angle of incidence we need to find phi I. It can be computed as tan phi I is equal to 750 over 300. 750 over 300 is 2.5. From this, phi I can be found by considering inverse tan. In the present case, it turns out to be 68.12 degrees. How tan phi equal to 2.5 has come into being? For that, you have to consider this diagram. Look at this diagram keenly. This is phi I, angle of incidence. This is normal. This part is 1500 by 2, 750. This side is 300 height. So tan phi becomes 750 by 300. That way, phi I comes out as 68.12 degrees. Now, it's a matter of substitution and simplification. Maximum usable frequency then turns out to be 18.783 megahertz. Another problem on skywave propagation, example 4. Determine maximum electron density in F2 layer if the maximum usable frequency FMUF of the layer for an angle of incidence 25 degrees is given as 18 gigahertz. So we need to find out maximum electron density. It is given that maximum usable frequency is 18 gigahertz for an incidence angle of 25 degrees. Solution. It is given that maximum usable frequency is 18 gigahertz. Okay. It is also given that angle of incidence is 25 degrees. This is also okay. The maximum usable frequency in terms of ionization density is FMUF is equal to square root of 81 Nmax multiplied by secant phi I. Notice the factor that is multiplying secant phi I is critical frequency. Critical frequency is equal to square root of 81 Nmax. The maximum electron density then can be computed as 18 into 10 power 9. This is maximum usable frequency. Square root of 81 Nmax multiplied by secant 25 degrees. 25 degrees is incidence angle. From this, after a little bit of manipulation and simplification, we can obtain Nmax as 328 into 10 power 16 electrons per meter cube. Now we move to another mode of wave propagation, that is space wave propagation. We consider some problems and their solutions. We begin with example 1. Determine free space path loss in dB undergone by a 0.2 gigahertz wave by the time it travels a distance of 1.5 kilometer in a medium with epsilon r equal to 2.25. Free space path loss in dB. This is what we are asked to find out. It is given by a formula. PL is lambda square over 4 pi r whole square. This formula. Lambda is wavelength, r is distance. Solution. Wavelength of 0.2 gigahertz wave in the medium with epsilon r equal to 2.25 is 1 meter. How wavelength is calculated here? Wavelength is V, velocity in the medium, by F. Velocity is C, 3 into 10 power 8 meters per second, by square root of epsilon r, this is V, into F. So using this formula, lambda has been calculated. It is found equal to 1 meter. So lambda is known. Distance is given 1.5 kilometers. Substitution gives us path loss as 2.81 into 10 power minus 19. It can be converted into dBs too by applying 10 log. Applying 10 log over to 2.81 into 10 power minus 9, we get path loss as minus 85.51 dB. Another problem on space wave propagation, example 2. A 25 kilometer microwave link is functioning at 9 gigahertz with antennas of same gain equal to 25 dB. If the power radiated by the transmitting antenna is 12 watt, calculate A, the path loss, and B, received power. This is the problem. A microwave link, it implies it is space wave propagation. Of course, from frequency also it can be understood that it is space wave. Now solution. The given wireless communication link is working at a gigahertz range, so it is a space wave link and the wave must be traveling in straight lines. Given that the link distance is 25 kilometers, here it is given 25 kilometer microwave link. Wavelength corresponding to frequency 9 gigahertz is 3.33 cm. So this is the information available to us. With this information, now we go and attack part A of the problem, path loss. PL is given by the formula lambda square over 4 pi r whole square. Lambda is available, r is available. Substitution and simplification gives us PL as 1.1 into 10 power minus 14 in dB. Also we can determine it by applying 10 log over 1.1 into 10 power minus 14. It turns out to be minus 139.57 dB. This one. B part, received power. We are asked to determine received power. It is given that the gains of antennas are equal to 25 dB. In absolute terms, it becomes 316. Gain in absolute value, 25 dB in absolute terms, absolute value, it becomes 316. So PR is PT, GT, GR, lambda square over 4 pi r whole square. This is phase transmission formula or its variant. PT is radiated power by the transmitting antenna, GT, GR gains of transmitting and receiving antennas, lambda is wavelength, r is distance, link distance. All these quantities are available to us. Substitution and a little bit of simplification results as PR as 0.01322 into 10 power minus 6 watts. Another problem on space wave propagation, example 3. Find the optical and radio horizons of an antenna with a height of 80 meters located over the surface of spherical earth. We are asked to determine optical horizon, radio horizon when antenna height is 80 meters. This is the problem. Solution. The visible horizon or optical horizon is given by this formula. D is approximately 3.566 into 10 power 3 multiplied by square root of HT where ht is height of the eye. Thus, for the given values, optical horizon becomes 3.566 into 10 power 3 multiplied by square root of 80. 80 is height of antenna. In the present case, antenna is acting as eye. Antenna is functioning as human eye. So D optical becomes 31.98 kilometers. The radio horizon, second part is radio horizon. It is given by 4.266 into 10 power 3 multiplied by square root of ht, where ht is height of antenna. Therefore, for the given values, radio horizon becomes 4.266 into 10 power 3 multiplied by square root of 80 equal to 38.15 kilometers. Notice in case of radio horizon, antenna is acting as an antenna. HT is antenna height. In case of visible horizon or optical horizon, antenna is considered functioning as human eye and HT is height of the antenna. Another problem, example 4. A space wave link consists of repeaters located at a distance of 40 km intervals. Find the minimum height of transmitting and receiving antennas above ground level. Solution. To give a link range of D, the heights of transmitting and receiving antennas HT, HR respectively must be. This is the formula. D must be equal to, or D is equal to 4 into 10 power 3 into square root of HT plus square root of HR meters. So this formula relates heights of antennas with link range. Both the antennas can be of minimum height only when they are equal. Thus, height of antennas is H, then can be found. Here, given that minimum height of transmitting and receiving antennas. This minimum happens when heights of the antennas are same. Let us suppose height of each antenna is H. Then D becomes equal to 4 into 10 power 3 into 2 into root H. Solving this relation, of course D is given 40 kilometers. D is available. Only H is unknown here. We get H as 25 meters. Another problem, example 5. A microwave link is functioning at a frequency of 10 gigahertz with a straight line distance of 60 kilometers between the antennas. If the height of the transmitting antenna is 60 meters, find the minimum height the receiving antenna should have, assuming the absence of atmosphere. Now we consider the solution. The given wireless communication link is working at 20 gigahertz frequency. So it is a space wave link and the wave must be traveling in straight lines. Okay. The relation that connects a range of space wave link to the heights of the antenna is given by this formula. D is approximately equal to 4 into root HT plus 4 into root HR, where D is in kilometers, HT and HR are in meters. Given that the link distance is 60 kilometers and the height of the transmitting antenna is 60 meters. Thus, the height of the receiving antenna can be found as, this is the formula. 60 is nearly equal to 4 into square root of 60 plus 4 into square root of HR. From this equation, HR can be found. In the present case, it turns out to be 2.693 meters. Another problem, it is also on space waves. Example 4. A VHF communication link is established with a 35 watt transmitter functioning at a frequency of 90 megahertz. Determine A, the distance up to which LOS communication may be possible if the height of the transmitting and receiving antennas are 40 meters and 25 meters respectively. LOS means line of sight. That is A part. Also evaluate B, field strength at the receiver end. Solution. It is given that communication link is working in VHF band and hence the wave must be space wave traveling in straight lines. Part A. Given that HT is 40 meters and HR is 25 meters, then range of space wave link becomes D is nearly 4 root HT plus 4 root HR. HT, HR both are given 40 meters, 25 meters. Substitution gives us D as 45.29 kilometers. B part. Here we are asked to determine field strength. It is given that the transmitter output power is 35 watt, wavelength corresponding to frequency 90 megahertz is 3.33 meters, intrinsic impedance is 125 ohms. Substituting the given values, the required field strength can be obtained from this formula. E is equal to nearly 4 pi HD HR over lambda D square, square root of P eta naught 4 pi. D is given, HT is given, HR is given, lambda is available, D is also available. It was found in the previous part of the problem. Substitution and a little bit of simplification gives us E as 0.015 volts per meter. With this, we come to an end of the present session. Hope the session is useful to you. In this session, to recap, we considered several problems and their solutions, which are based on various modes of propagation of electromagnetic wave, ground wave, sky wave, and space wave. We meet again with a new topic in another session soon.